actually very easy once we have our tools. So we have finite fields, and G connected. Just to say something, this is very important because the f points of G, of course, R or E, form a finite group, and those are called, if G is semi-simple, those are called groups of Lie types, finite groups of Lie types. And actually, classification tells us that most simplified groups are of this form. So those groups are extremely important to group theory. And indeed, Lang theorem has many implications. So I will not use any of those here, but actually I don't study finite fields, but I cannot just walk by. So I guess I will keep it. I'll guess that I will. G now will be algebraic. So maybe let's go on with it. Sorry for this presentation. And the claim that 8.1 is true. And this follows from this lemma of Lang that says that following map over that's y closure of f x goes is many times called the Lang's map. Phi x, phi is for me, so I write down is project. Well, phi is the generator of gamma. Basically, as we know, Galois groups of finite fields are always cyclic. The absolute Galois groups are actually generated by the Frobenius map, which is raising things to the power of the characteristic. Right? And
so gamma is now.
yeah, so I changed the notation. Gamma is the Galois group. G is the algebraic group. I guess I hope I will not.
No, but gamma is only the algebraic closure. The Galois group.
Gamma is the relative. It's the Galois of E. This is a final.
Because there is no E in this statement of the lemma.
Oh, the lemma. Oh, sorry. Well, phi is a generator. Is the Frobenius. Actually, any of them. And actually, what goes into the proof of the lemma is the fact that phi, unlike in characteristic 0 here, automorphism of the field is actually an algebraic map. Raising things to the power of q is a polynomial. So I will postpone the proof of it, but I will be strongly using the fact that phi is, or this map is algebraic. Okay? But now I'll explain first how the lemma implies the theorem. Now I'm assuming this actually, so yeah. But they want to view phi also as an automorphism of f bar. And take cocycle. So a cocycle is a map gamma to G that satisfies the cocycle equation, and of course it has its value on phi, and everything is given by this value. Let me. Stress is phi. That's the lemma. Tells me that a phi is an element of G, could be written as some x inverse phi x, when x is like that. So this is the co-boundary expression, right? So actually, if I had this with x in E, I would be done. Then this is I guess because I can a priori a phi takes values in GE. If I view it in GF bar, F bar is also a notion of phi, of course. If I view it in over F bar, I could view it as a co-boundary. This is what Land's lemma tells us. And now, let's do this simple computation. Let's look what a phi squared is. The cocycle equations tell me this is a phi times phi of a. And let me now substitute this is a phi times phi of x inverse phi x, right? And you see the cancellation here, so it's x minus 2, sorry, x minus 1, phi squared x. And I guess I'll skip the next line, a cube. I claim that induction, if you wish, here it is. And say that say that by end the degree of the exception, of course, a phi n is a phi n is a1 plus a1. On one hand, on the other hand, this is by this induction, it's x inverse phi x. But then you see that x is phi n x. So x is in the fixed point of phi to the n. What is the fixed point of phi to the n? Just tell me. And we are done. And so this co-boundary expression actually takes place for two. And this is the proof. And now, any questions? consider. Okay, now, so the lemma is not about fields of definition. It's just about points over the algebraic function. So we have this algebraically closed field, and we have this map. So X inverse some automorphism of the field of finite order, and so not finite order, and the claim is that this line map is on. Now consider. So I guess when I write G now, I'm having in mind the points over the algebraic function. Consider the G action on G. So G is a group. Consider G as an algebraic variety at the point by G, given by. So this is variety. Given by X, maybe G acting on X, I'm defining this action.
Sorry, I'm confused. Okay, can I go back?
Yes. Okay. I mean, put this. We go back to the proof of the theorem.
But phi to the n is identity anyway, right?
Sorry, it is the identity over E. This is what I. So think of say F is F sub P sub Q, and you have this is F. You have E is you have E over here.
It's all.
Okay.
See.
I want to give it a minute. Let me anyway say it. The extension of FP of degree n is exactly the fixed point of x to the p to the n. This is a field extension, the field extension of the unique one of degree n of f. Right. So it's exactly and this thing is field x. Okay, confusion solved. Okay, now I'm in the proof of the lemma. I want to prove that this map is on. So I'm viewing this map. Actually, I'm viewing this map as the orbit of the identity under a certain action, a group action. So I'm letting G act on itself, but I see it will not be the standard conjugation action. It will be conjugation. Well, G act on itself from the left, G act on itself from the right. Conjugation is just the diagonal action. This is a G times G action, and I will stick to the diagonal. This is conjugation. G act on the right also after twisting this thing, which is an automorphism. So this gives me another G times G action, and I will take the diagonal there. So let me define it. Only the way it is written here, it's not an action, it's an anti-action, so I make a slight change. So this would be G of X. Let me erase this product. It's confusing. PG inverse. Do we agree? Again, I'm thinking of G as the group element, X as the point, and do we agree that this is a group action? And the thing is, this is an algebraic function. So it is defined by polynomial. So the algebraic here is not an adjective of the group, it's of the group action. The action is defined by polynomial. Of course, this is an algebraic variety and an algebraic group. This is an assumption, but also this action is given by polynomials, and I can use whatever we did to study actions in the past. So let me ask the question. What is I want to say something about the orbit structure of this action. Actually, I want to say that there is one orbit. Right? This is what I'm doing. So instead of looking at orbits first, we look at stabilizer. What is the start of x? What I will show is finite. And so Lang's original proof uses smoothness of some actions and some conceptual but trick computation. The proof I will present is more tricky, but actually very elementary. So first of all, now I fixed an x. Every x in f bar. F bar is just the union of increasing fields, or increasing finite fields, right? Every element is algebraic over f and sits in a finite field itself. Find m such that e to the mx is x. You can do that. And so again, maybe. Okay. Is that clear? Or shall I? Okay. And now consider y, which is x, dx. Why am I doing it? It will be clear in a few minutes. Take this one. Maybe I'll write this x sits in some in G E. No, it's not saying G K. K over F finite. Now, of course, this this sits in some GK as well.
In MS, the order of the color.
So yes, yes. Maybe it's, I'm not sure. Which is a finite group. The thing is, I'm looking at this element. This is a group element. It sits in some. It is defined over some field, which is finite. So it sits in the k points of some of the group. So this, all in all, this is a finite group as well. So let R be the exponent of y. So that means y to the R is 1. So actually, just maybe I'll say differently. G F bar, the group G itself, the F bar points of it, this is a locally finite group. Every element has some finite exponent that taking R to be the exponent of y. And now, look at the following. I'm asking myself, assume G is asking myself this question. X is fixed, I'm asking what are the G's that do that. So just to rewrite this means that G is an X conjugation of phi G. So let me call this function of G depending on X, Fg. X is fixed again in this discussion. And let me ask, what is F2 of G? Let's do F is that one. So I should feed that and conjugate. If I feed this, you see I'm doing X, this is the conjugation, and now I'm feeding. So it's phi X, phi squared G, phi X inverse. And now I'll do it K times to see what's happening. Then of course by induction it will be X, phi to the K. Oh, I think yeah, -1 X. Phi to the K, G, and same inverse. Lastly, I will do it now mk times. Mk is still an arbitrary number. K will be R. So let it do MR times. So now, if I do it n times, what I'll get here will be y, right? Now, the next guy that will come in, if I do it k plus n plus 1 times, will be phi to the n, which is which was chosen to be yes. So it's a periodic thing. So here I will get y to the k, and this is what will come in the bottom here, and y to the k inverse, and in the middle I will get that. Agreed? And lastly, I will specialize for k to be r, because r is the order of y. So this will just be phi to the mr of g. So iterating, I'm getting my f is just phi, and now basically I'm done. Just write it down. So the stabilizer of G, of X, sorry, is all those things that are fixed point of F. And obviously it is included in the fixed points of f to the mr, which is the same as the fixed points of phi to the mr and this is the equation defining some finite field extension. Particular so what we proved so far? So we define this action of the group for the variety, and we proved that the orbits are always finite. Oh, sorry, stabilizer. Stabs are all. This was remind me, for an arbitrary x, I showed that the stabilizer is finite. Are all well 0 dimensional. of full dimension. dg. Right, dimension of the orbit is dimension of G minus dimension of the stabilizer. Yes.
Why is the so dimensional?
They are finite. I'm walking now over the algebraically closed field, right? There's, so if a group of over algebraically closed, the points will have finitely many points if and only if the group is actually finite. Where am I? Okay. Now I'm looking at the again. Remember what I'm claiming. I'm claiming that there will be just one orbit. The method again with the study is subjective, but now consider the orbit of E. So its closure first of all, it is of full dimension, hence it is open. It is an open subvariety. But what is its closure? It's its closure. Its closure, as usual, consists of lower dimensional orbits. So this is a general fact. Now, again, we are walking over an algebraically closed field. So this is a general fact about group functions and varieties. The orbit closure consists of lower dimensional orbits. But all orbits are for full dimension, and hence it
So the boundary,
should be closed to begin with.
the boundary consists of
It's boundary. It's boundary, and hence it is empty. There is no boundary. It is open and closed. It is open and closed. And closed. And G is connected. This was the assumption we haven't used yet. Implies it is empty. So this means G is, I think, I want it like that. Or if I invert those things. Take x inverse. One over all the x inverses to make it fit. What we wanted, this one, this one. Okay. So this is it. Let me give you some overlaps. I will be a bit sketchy. But are there any questions about the proof? So the following is a beautiful corollary. Maybe you've seen the proof before, but not that conceptual. What is it?
so
we say this in this terminology? We prove many things about orbits or affections on varieties.
So
Did we prove this?
yes, we
But
proved
maybe
this.
you said it-
So no, we said. If I remember correctly, we said just that. So we
I
actually
know the orbits are locally
the orbits are locally closed.
locally close.
Yes, and
That
so
I remember, but
maybe this I don't remember if I did prove it explicitly or just mention it, because this is not part of the theory that I'm exploring in this course. This is part of the standard theory of algebraic groups.
I know. I'm just
over-
wondering whether it easily follows from locally close and just not seeing it, or whether there's an additional step
Just
that we did not do.
topologically, I mean, if you just don't want to do algebraic geometry ever, you are given that the orbits are locally closed and you want to deduce that they are of low
What is
dimension.
that?
I don't know how to.
Yeah, but it's not like just one sentence.
It's given the previous sentences said correctly. This is one sentence. I mean,
Okay, go on.
this is I think the first section. This is proven in the first section of any recent book in algebraic groups. Okay, this is definitely very standard stuff. As usual, standing here, I cannot provide a proof of this one. But maybe I said it.
No, you say, but it is,
Hmm?
but it is in the section of Humphreys at least.
Yeah. So Humphreys, it doesn't prove, but it is correct that Humphreys is written in the book in that way. So okay, maybe I can record it and tell you the proof of that. Look at point. Now, the claim is every finite division ring. Ring. So there is there are proofs for this by counting, but quite sophisticated. The proof that I'm presenting, maybe it's not the most simple, but certainly very conceptual. Let's write it down. So let D be finite division ring. And I want to view it as a central simple algebra. So first of all, I'm looking. My F will be the center of the observe. That the center is well distributive and contains instances of whatever, so it is a field. And D becomes a central division algebra over F. Speaking of F field, I will walk over that one, of course. And now we pick E over F a splitting field for D. So I need you to know something about the theory of division algebra, but this is not about finite division algebra. So that there always exists such a guy E, such that over E, over F, sorry. Yeah, over E, it looks like a matrix algebra. This is a general thing of central simple algebra, or in fact, for division rings, D will be of some square dimension of it will be some n square dimensional over F, and any maximal field in it, any maximal commutative sub algebra will be obviously a field, and it will be of dimension n, and it will serve as a splitting field. I'm assuming these are not hard paths in any case, and I want to be sketchy here. So this means that D is a form of Now, what is, I'm thinking of algebras. What is the automorphism as an algebra of M and E? Who knows? So this is my G. This is a connected group over this finite field E. So now D, my D, is an element of the descent set algebra split over F of F. What is my F? Split these guys. Take the algebra, which I know to be isomorphic to page 1 guy. Which I know to be linear. Oh, and also M and E. M and F, sorry. So these two guys are the same. They're F isomorphic. Make sense? We're not done. Just one more step. What is the step? This division plane. Here we have zero divisors, so unless n is 1. So there are many other corollaries of this Lang theorem that are in the classification and the study of quadratic forms and bilinear forms of the finite fields. As we said, bilinear forms over finite fields are always given by forms of some algebraic groups, and we know quite a lot about those by Lang's theorem. So I think I will leave it to some of you, maybe to explore it further in this direction if you want at some point. If some of you want to, I don't know, submit a work or present a lecture. But now I do want to make, I mean, what is the time? 20 minutes. So for this class, 1 hour. So I do want to present one more corollary, which is important for algebraic groups. So G connected. Algebraic group over F finite implies G is, I haven't defined it yet, I will define them in, G is one state. I need to make a definition and then to prove something. So maybe I will mention the fact. So remember that for solvable groups, I said that the group is split if it is it has the composition series with additive and multiplicative of the field. I said that it is anisotropic if you can't find any such, and it is isotropic if you are in between. And this is just a reminder. For reductive groups, I'm using usually the terms split, isotropic or anisotropic with respect as synonymous of the maximal torus. There is a maximal torus which is such. Okay? So there is a fact that I'm just reminding now, again, of the standard algebraic groups. Every group, every F algebraic group has a torus, the maximal torus. Defined over F. It may be split, maybe not, I don't know. But not so what about Borel subgroups? Sometimes you do, sometimes you don't have Borel subgroups defined over the field, regardless the question of splitness. So here comes a depth. G is said to be quasi-split if there exists Borel subgroup defined over the field. And as some of you definitely know, when I say in the study of algebraic groups, of reductive algebraic groups in particular, somehow one can there is an induction, there is a way to study it by inducing things over, say, representations of groups, etc., inducing over parabolics, over Borel subgroups. So this is sometimes you cannot find any Borel subgroup, and then you are in a problem. I mean, of course, when you do work over an algebraically closed field, this is not a problem, and nothing here is an issue. But the claim is that of a finite field, I'm not saying that the Borel group will be split, but there exists a Borel group which is defined over the given finite field. So let me, questions about it?
No, but I'm confused about that too. Didn't you just say, when you say an algebraic group is K-split or S-split, what do you mean? You mean that the maximal torus
The maximal torus, yeah, so that's...
is defined over this field?
So, no. So always, so this was the first part, just for, again the first part, well, for two reasons. Also I will use it, so it was a place to remind it. But I gave it basically as a reference, as a comparison. I can always talk about a maximal F torus. There exists. And then I can discuss whether it splits or not. And regard these as a property of G. Okay?
Well, you can talk about a maximal F torus, but if this maximal F torus is also a maximal torus for the algebraic closure.
So there always exists the maximal torus for G itself, over the algebraic closure, which is defined over F.
So what is F split then? I'm totally confused now.
Take O2. Okay?
No, I not the example. What is the... Please
Okay.
tell me what is actually...
Can I find, okay, so I'm saying, I guess I said it aloud, I
I would
didn't
have
find out.
taken this as the definition of split group.
No, the existence of a torus which is defined over F, assume there exists a torus which is defined over F. It might be an anisotropic torus, like in here, and it might be a split torus.
Now, when you make maybe I misunderstand what you mean with maximum. When you say maximum, I mean in the algebraic closure.
Yes.
Okay, so what does it mean to have a split doors?
To have split doors?
Yeah.
A reductive of over F is said to be split if there exists T in G such that T, first of all, is defined over F. This is, but this is not yet the definition. I mean, such exists in any case, and you can find such a guy. Then I can ask myself about the F points, or maybe T is F isomorphic to Gn to the n over F. In particular, the F points are just F star to the n. Over F, this is a standard torus.
Yeah, this is what I mean when you
So
say
the
maximum
defi-
torus defined over.
No, defined over F is defined by F equations. O2 itself, just doing the real group. This is a, okay, think about it as a complex group, and in it, the obvious real group. This is defined over R, but it does not split over R
Yes. Okay.
itself. I mean, sometimes
So you-
G might be a torus itself. G might be a torus, but not a split torus. Then obviously G contains a torus which is defined over F, but it need not split on over F.
Thanks. Okay, so you have to distinguish between F torus and defined over F. Torus defined over F. These are two different things.
Yeah.
Yeah.
I won't use the term F torus. I would use the term split over F.
Yeah. Okay.
Defined over F and split over F are two different things. I mean, split over F definitely means that it defines over F plus more than that. Over F is standard. Okay? And the fact that, it is not really a fact, but it's very standard, that tori do define always over the field of definition, maxima tori. I can, in the variety of maxima tori, I can find a torus which is defined over. In the variety of Borel subgroups, sometimes I cannot. If my field is nice, then I can. For a finite field, I can. And this should follow this corollary. In that case, I would say that my group is quite split. And over finite fields, all groups are quite split. This is the case. And of course, I mean, I added connected here, but I would say that the group is quite split if its connected component is quite split. So, in short, the slogan here is over finite fields, all groups are quite split. So let me give you this. Show you. Oh. So take B and G. Go ahead. So a priori, as everything else, it is defined over F down. So this means nothing, but it means that it's not assumed to be defined over F, of course. And phi B, phi is the automorphism defined here. F is a fixed point of some automorphism, and I'm using the same notation as before. Phi is this automorphism. So phi is So, can you recall the definition of Borel? A Borel subgroup is a maximal symmetric solvent subgroup. Of course, phi b has the same properties. Phi b is Borel as well. Phi b is Borel. It is defined in group-joining terms, and phi b is Borel. And again, I'm using in fact the fact that phi is algebraic. This is an algebraic subvariety, another algebraic subgroup of G. I'm using this implicitly. In the theory of algebraic geometry over finite fields, I mean, you get used to it. You don't mention it anymore. Hence, conjugated to be. All Borel subgroups are conjugated. Side, yeah. So there is this G in G F bar, such that I can conjugate back to B. Now I'm using Lang. In fact, I'm using Lang's lemma, not the theorem itself, to express G as X in Lang's lemma. Find such an X. And I will take B prime to be that conjugation of B. I claim that this guy will be my F defined one. So let's try to understand what is phi of B prime. So this is phi x, phi b, phi x inverse. Good. Phi x, this one is xg, right? So this is xg, x inverse, and now this is conjugate by g of db, so this is x dx inverse, which is so b prime is phi stable x prime defined of So yeah, I want to start now with the Borel-Serre theorem. Maybe I will.
So how does it prove the G?
So a subvariety will be defined over F if and only if it will be stable under the Galois. Because this, well, I use it over and over. It's part of the term. So, and this is what we do. I want now to make to stop discussing finite fields. Again, there's a lot to discuss further, but I want to discuss local fields again. And let me start. I'll state a theorem. Maybe say a word or two, and then we take the break. So the famous theorem of Borel and Sayer says that if f local of characteristic 0 G algebraic group defined over F, then H1 is fine. And before the break, I will explain. There are many applications for this, but I will explain why it's important from the point of view that we studied earlier of orbit structure of an algebraic group and an algebraic variety. As we said, and used a few minutes ago, when over algebraically closed field, if an algebraic group acts on an algebraic variety, the orbit structure is very nice. Every orbit is locally closed, and the closure of the orbit consists of orbits of lower dimension. We've seen that over a local field, actually without characteristic assumption, and more generally over complete fields, the orbits are indeed, in any case, locally closed also for the F topology. But this finiteness will tell us further that each group orbit over the algebraic closure actually split further into finitely many orbits over the smaller field. Maybe before putting the corollary, let me remind the example, the same example basically I'm giving over and over because I think it's very illuminating. Let me consider GLNC over ON. So this is, you can think of this space as a space of complex, bilinear, non-degenerate, symmetric forms. Of dimension n. ON is the stabilizer of the standard one. And actually, over the complex number, over the algebraic closed field, in general, all bilinear forms, non-degenerate one, are GL equivalent. Up to a change of basis, they're the same. But so, in particular, though, this is a complex variety. It's a complex analytic manifold, and I can look at its real points. I can look at the orbits of G and R acting on it as a whole. But of course, I'm interested mostly how does it act on bilinear forms which are defined over R. So again, if you take over R in Rn two different bilinear forms, symmetric, over the complex number I can always conjugate those, but maybe not over the real numbers. So now let's discuss those which are real. And the claim is that this is a union of GL and R, well, over the stabilizer of the various standard forms. So this is OPQ, T plus Q. OPQ is defined in the subgroup of GLNR stabilizing this standard form. Okay, so this is and the thing is these are finite many orbits, and we know this very well in this example. And of course, by the way, there is just ones and minus one here. and somehow this is related to the fact that the Galois group is of order 2. This, so maybe I should say, one can prove this, the fact that there are finitely many orbits directly for the rings. There is a term called Uri Bader, saying that if you have a complex analytic manifold, then its real point is a real manifold of finitely many components. So I can use this one in order to prove the theorem that I'm about to write down in a minute, and actually use this in order to show the finiteness of the Galois cohomology for the rings. But the following is a general fact that is correct over an arbitrary local field of characteristic 0. If G act on X transitive, or maybe I'll call it V, transitive action on a variety, so algebraic action of an algebraic group of an algebraic variety of things defined over F, etc. Then I can look at XF like that one, and divide and look at how many orbits I can see this. I can see it. Divide by GF, and the claim is fine. So of course, when I have a general action, it decomposes nicely over the algebraic closure into orbits. But every orbit now decomposes further this is into closure of G F bar. But over F, over closure, every orbit decomposes further. The claim is that decomposes further on only into finite magnitude. So this is very useful fact, and the proof of it is this exercise that I gave you at the beginning of the previous lecture. I'll write it again on the board, just to remind you when you get the break. This follows, well, so GF modulo HF, mainly rewrite this V as G mod H. No. I wrote previously BG, B was an abstract G group, and A. I wrote this. There G was the Galois group yet. Now the fixed point B is G, and G is the Galois group, sorry. And the fixed point is GF and HF. And this is the same, or this is in particular a subset of H1. Galois H.
What's H?
Sorry?
What's H?
So I guess that this means that the fact that G is transitive means that I can take H to be the stabilizer of a point in V. Take any field here, and you have a natural map onto from G mod H to V. So if you want to show that there are finitely many orbits here, it's enough to show that there are finitely many orbits here. So I'm presenting things across the space. And sorry. I wrote things corrected me. I didn't write it the way I should. It should have been G on H, F, G, sorry. That's the exercise we had. That's a corollary of it in that particular case. And if this is finite, then this is finite, which provides a corollary.